Physics 2211, Lab 4 on oscillations. The purpose of the lab was to observe the oscillations of an object on a spring and create a model in Python to simulate the movement of the object, compare the results of the model in the observed experiment, and then plot energy changes as computed by the model in a graph. The result was that while the model remained a decent indicator of the motion of the object throughout the approximately 10 seconds of the clip, it was further and further off by the end of that time. So some of the models and physical principles used in the lab include Newton's second law, the momentum principle, as well as the velocity update formula and position update formula derived from that. And then for forces, we have the gravitational force, which is given by mass times g, and Hooke's law, which gives that the spring force is equal to negative the spring constant times L minus L naught times L hat. The period of oscillation of a spring, T, is equal to 2 pi times the square root of m over k. Then the energy principle, which is that the change in energy is equal to the work done by the surroundings plus heat transfer, and that the change in energy within the system, given no outside forces, remains the same. Then we have the formulas for kinetic energy, 1/2 times mass times velocity squared, gravitational potential energy, which is equal to mass times g times the height, which in this case is the y direction. Spring potential energy, which is given by 1/2 times k times s squared, where s is L minus L naught. So analyzing the video and tracker, the system was the spring and the object hanging from it, and the surroundings included the air and the hand that released it. I used tracker to take note of the motion of the object with respect to the origin, which was the attachment point of the spring. The initial position with respect to that of the object was negative 0.112 meters in the x direction and negative 0.633 meters in the y direction. And the initial velocity was 0 as the tracking started from the moment the object was released. And this data was downloaded into a CSV file to be uploaded into the Python program later. So in GlowScript, we used initial conditions from the pre-lecture video, including the ball mass and L naught. We used the ball position, initial position, initial velocity given in the previous slide, and then the formulas for energies given in the formula slide. We also found the spring constant by estimating the oscillation period by using the tracker data and using the period of oscillation of a spring to find the spring constant. Then over here, right after line 100, we calculated the gravitational force using the force formula, the spring force using the spring force formula, and then the net force by adding the spring force and the gravitational force. We then use the position and velocity update formulas to update the motion of the object throughout the simulation. And then we use the ball position to find the position of to find the position of the spring and where the object was using which was given by L and L hat. And then we updated the energy changes by using the same energy formulas and subtracting from the initial energies, which were given up here. We also updated the final time to be 9.402 seconds. So these were the graphs generated by GlowScript. As you can see on the right here, we have our x position versus y position, or x position versus time and y position versus time graphs. You can see at the start, the model was a very accurate prediction of the movement of the objects, but as time went on, it became a worse and worse prediction of the movement. And some factors that could have been affecting this include air resistance and other damping forces that weren't accounted for in the model, and error in exact tracing and tracker, because it was just done by a human, me. And then we have our change in energy versus time. As you can see, delta E, the change in total energy, remains right along the x-axis there, or time axis, I guess in this case, despite the movement of all the other energies, which is important because our first what does it mean question is the energy principle satisfied? And we can say that in the model it was satisfied because the total change in energy remains at 0, and it was as well in the and it must have been as well in the experiment, because we can see that despite the fact that it doesn't appear to be in the graphs, we know that some force was being exerted by some outside forces were being exerted, probably some air resistance, which means that there was work being done on the object, so the energy principle is still satisfied because that change in energy is equal to work done by the surroundings, plus the heat transfer. And then the difference between oscillation periods, the Y oscillation period was 1.52 seconds, and the X oscillation period was 1.61 seconds. And the main factor in the difference between those is going to be the gravitational force acting in the Y direction. And that difference is why we don't just see one circle here or one oval, and we see instead that the oscillation moved around inside of this rectangle.